Sir, you are muted.
Yeah, I am unmuted now.
Yeah.
So thank you, Senthil Kumar, for the introduction and for the invitation to this webinar. And all right, we are late by about 20 minutes due to delay in my laptop and my communication. I'm sorry for that. And so let's start right away. Mr. Shailesh, we can start with the slide number 8. You can just skip the first 7 slides. Because all these are video contents, they will not be played right now because you don't have those video data. So all these slides meant that whatever may be the process of casting, let it be sand casting, gravity die casting, LPDC, HPDC, the common factor is liquid aluminium. And we are into field of engineering casting. So naturally that liquid has to be at perfect condition. And this total webinar is dedicated to melting and metal treatment of aluminium. Why? We will understand in coming slides. So to get the liquid, one must melt it by energy inputs, whatever it may be, let it be fuel-fired furnace or electric furnace. Next slide. Principles of melting are melt it as quickly as possible. Melt a metal with minimum energy input, achieve complete solution, melt it clean, keep it gas free and minimize the melting loss. Next, please. We all know that there are furnaces required for melting the equipment, which are classified into 2 categories: direct heating furnaces, which are Kleiner furnace or rotary furnace, and indirect heating furnaces, that is crucible type furnace, lift up crucible, fixed crucible or tilting crucible. Next, please. Advantages of direct heating are very quick melting because the flame is directly in contact with the metal. Bulk melting is possible. Tons and tons of liquid pool can be made available. Low fuel consumption and good alloying due to higher temperature ranges. Next, please. The disadvantages of direct heating are high melting loss, oxide generation, which leads to inclusion, and loss of nucleation is the biggest loss. Then loss of magnesium or zinc or other volatile materials, and poor control on temperature. One might have noticed that in direct heating furnaces, the temperature of the top face of liquid pool is at least 30 to 50 degrees higher than the bottom of the liquid pool. So temperature control in direct heating furnaces is very poor. Next, please. In case of electric heating, there are 2 means, that is induction melting and resistance melting. And resistance mode can be used for holding the liquid metal in liquid condition as well. Next. Features of induction melting as it's a very fast melting because energy intensity is very high in the crucible. Good alloying due to the churning. But again, the bad effect is that due to churning, high gas pickup occurs and also oxidation increases in it. Another disadvantage of induction furnace is that you need a separate holding furnace for metal treatment. Why? Because the lining of induction furnace, which is used for aluminum melting, is usually neutral or basic lining. And these linings get attacked by the fluxes which are used in aluminum metal treatment. We will come to that in a later stage when we see the aluminum metal treatment. Next, please. Resistance heating is slow melting, but we get an advantage of precise control on temperature. I have seen furnaces with plus or minus 2 degrees Celsius control available. Melting cum holding in the same furnace is possible. Treatment in the same furnace is possible. Next, please. Melting loss is a cost element because aluminum is very prone to oxidation as it is very high in galvanic series and it readily oxidizes. And when the molten metal is in contact with ambient air, that oxide film once formed is actually impermeable and it remains steady. But we have to bail out the metal, we have to take out the metal, scoop it out by using our ladles. And during every scoop out, we are compelled to disturb that oxide film and fresh metal comes in contact with the atmosphere. And that's why new layer of oxidation is formed. That leads to melting loss. Next, please. Depending on the condition and hygiene of the foundry, it may range between 1% to 10% of the liquid metal available. Tips to control melting loss: melt and hold at lowest temperature and for a shortest time. More the holding time, more is the melting loss. Cover the melt by cover flux to protect or prevent it from the air contact. Do not disturb the oxide film once formed and dispense the metal in shortest time with least exposure to air. Next, please. Now from here, our real session starts. To have good quality castings, we must have good quality liquid metal. Any liquid metal has got many unwanted parameters in it. They get induced due to the process and the environment. I don't say that the ingots or the base metal is dirty, but during process of melting, it attracts oxide and gas pickup, and that's why we need to make it good, make it correct in order to get desirable effects in the casting. The process of correcting this dirty metal is called as metal treatment. Next, please. Now, why to treat metal? To remove dirt or inclusions, to eliminate dissolved gases, to nucleate metal for better solidification, to improve microstructure of beta or eutectic silicon. These are the four facets of metal treatment of aluminium. Next, please. Conventionally, there is a sequence being followed in metal treatment, which is first is cleaning or cleansing. Second one is degassing. Third is grain refinement. And fourth is modification. But when we are using inert gas like nitrogen or argon for degassing, then degassing, grain refinement, and modification. All these three treatments can be conducted together. But cleaning has to happen initially. The first phase must be cleaning or cleansing. Next, please. Yes. Now we come to the metal treatment number 1, the first phase of metal treatment, that is cleaning or cleansing. We have seen in the initial slides that during melting, aluminum gets oxidized. And okay, I need to correct this slide. The oxidization can be controlled to less than 1%, but if not controlled, it can touch or it can become 10% also. I have seen both the ends in my career at various locations. There was a foundry which had 10% melting loss, and there are foundries which have 1.2%, 0.8% melting loss. So as a thumb rule, you can consider that oxide is going to form necessarily, compulsorily. Now, aluminum oxide is spongy porous in nature, and along with itself, it gathers a lot of liquid metal in it, and it remains suspended throughout the depth of metal. Why it remains suspended? Let us understand. In case of ferrous materials or copper-based alloys, the density of metal itself is more than 7. With copper alloys, it is 8.5. With ions, it is 7.8. Whereas the density of oxide of those elements is very low. Iron oxide density is to the tune of 3.2, and copper oxide density is to the tune of 4.5. So there is a vast density difference between the oxide of that metal and the metal itself. But here in case of aluminium, the density of aluminium in solid state is about 2.6 to 2.65. I'm talking in terms of grams per cc. The unit is 2.6 grams per cc. And the aluminium oxide, its density is to the tune of 2.3 to 2.4 grams per cc. So the difference is nominal. It's not 2 times or 3 times the difference as in case of iron oxide. Now here, the nature of aluminum oxide is like a sponge. Just imagine you are throwing a sponge ball in water and stirring it. So the sponge naturally absorbs water in it. Just like that. Aluminum oxide, being spongy porous in nature, it absorbs liquid aluminum in it. And now this composite, which is a network of aluminum oxide having liquid aluminum within it, its density becomes quite comparable to liquid aluminum itself. And that's the reason why aluminum oxide is found right from the bottom of the crucible up to the top of the crucible. So, unlike any other metal, separating aluminum oxide from the liquid is extremely difficult. It remains suspended throughout the depth of the metal. Next, please. Next. Next. Now, first two were videos wherein I was breaking oxide lump by my hand and showing that there is liquid aluminum which is now solidified. But unfortunately, due to the problem with my laptop, I cannot show that video. I'm sorry for that. Now, the photograph which you are seeing is the oxide lump. If you have aluminum oxide collected in some bin, it's usually a practice in all foundries that they collect aluminum oxide in a tray or in a bin or in a trolley. If you find that the oxide is quite heavy and lumpy, then it means that there is aluminum metal embedded in that oxide. It's called as a heavy oxide dross, and that's a sign of poor metal treatment. A good dross or a good metal treatment sign is that your dross or your oxide should be like a powder. Next slide, please. Now, why to remove this oxide? If this oxide is not removed from the metal, it comes into the casting as a defect called as oxide inclusion. This oxide inclusion also attracts fair amount of gas, and it can catch air also, not only hydrogen. So oxide inclusion is a major defect, and it's a major cause of rejection. The fluxes like coverall effectively remove the oxides and further prevent fresh oxide buildup. Next slide, please. In this slide, you can see that just after machining, there are oxide inclusions and the films of oxide being revealed. Next slide. This is another photograph of bifilm oxide inclusion. Now let me explain what this bifilm inclusion is. Just imagine that oxide of aluminium is forming a film on the top of molten aluminum surface. Now compare it with tissue paper. A tissue paper floating on water surface. If you try to push your hand through the tissue paper, that tissue paper will first get folded, it will get rolled, and then it will break. The same thing happens with aluminum oxide film, and a multiple layer structure of aluminum oxide, just like a crumpled paper or a folded or a rolled paper. Such a structure of aluminum oxide is seen. This very structure is now visible in front of you on the screen. This is called as aluminum bi-film inclusion. Next, please. This is a microscopic display at 100x magnification of a bi-film inclusion. Next, please. This is a fracture showing a triangular surface on your right-hand side. On the right-hand side of the picture, there is a clear-cut triangle, which is a dark dotted triangle. And that's the oxide lump embedded in the test bar sample. Next, please. If we are into the field of engineering castings, we expect some mechanical properties out of the casting. Those mechanical properties can be predictable only when your casting is homogeneous from one end to other end. And aluminum oxide is something which disturbs that homogeneity. And hence, it is very important to remove those oxides by the first metal treatment, first phase of metal treatment, which is cleaning or cleansing. Coverall fluxes are usually mixtures of sodium chloride, sodium fluoride, potassium chloride, potassium fluoride also, and cryolite, etc. There are many manufacturers, they have many brands. I am not marketing any of them. Those manufacturers have their proprietary mixes for specific application, and it should be used in recommended percentage, partly during charging and partly after melting. These fluxes break the sponge network, and due to the exothermic reaction, the embedded metal drips down to merge with molten metal into the furnace or crucible. This leads to powdery dross, which floats on the surface momentarily. And a part of this flux, which is chloride, the chlorides get converted into a liquid flux cover, which is a sticky liquid just like honey. And this powder, which momentarily floats on the surface, it gets caught into that liquid flux cover. So that's how we are able to separate aluminum oxide from the aluminum metal. Next, please. Okay, this was also a video which unfortunately is not playable in this case. A person is putting some cover flux or coverall flux into the crucible and then churning it, then separating the dross. Next, please. This is a powdery dross. Again, it was a video, but you can see now that it is not lumpy. This powder is taken on my palm. Just like we take supari or some churan on your hand, you can see and imagine that it's just a spoonful of aluminum oxide. It should be as powdery as this. Next, please. Now, we understand that we do not want any oxide in aluminum liquid. But can we predetermine that our liquid metal is free from oxide before casting is made? The answer is yes. There are not only one, not only two, there are three methods by which we can determine or predetermine the inclusion level or the cleanliness of the liquid aluminium. Next, please. The first method is K mold. K mold is a Japanese invention. It has got a worldwide patent, which is still valid. I have seen many foundries using a duplicate K mold, but it is a wrong practice to use a duplicate K mold because you are violating the intellectual properties. It's a research of some scientist, and if you are not buying the original equipment, then it's injustice to that scientific study. Original K mold is available in Indian market at less than 30,000 rupees. Along with its validity certificate, that certificate is valid for lifelong. Whereas duplicate K mold is available for to the tune of maybe 3,000 rupees to 10,000 rupees. So instead of saving those few thousand rupees, go for the original one, because if you are caught with a duplicate K mold, then there are heavy penalties for that. Next, please. K mold is a practical method, shop floor method. The metal is poured into the preheated mold, which is like an inclined plane, as we saw in the previous slide. The mold has 5 notches and the test samples like flat bar. This is taken from the research paper itself. That's why it has got all the dimensions. 240 by 36 mm by 6 mm thickness are obtained. The test sample need to be broken at the notches and put together as shown is the next slide. The fractured surface are analyzed either visually or by image analyzer under low magnification of maybe 10x. Rapid solidification of the sample produces very fine matrix. Since it's an inclined plane and a 6 mm thickness die, 6 mm thickness casting in a die, solidification is very fast. So grains are very fine. And thus the inclusions are clearly visible and clearly detected by visual inspection itself. The number of total inclusions noticed per surfaces. That is, if now it has got 5 notches, we are breaking it at 5 places. So naturally 10 surfaces will get exposed. And in that bundle, if you find 10 black dots, that is 10 number of inclusions, then you see 10 inclusions over 10 surfaces. So 10 by 10, the K value will be 1. If you find 5 dots of inclusion in those 10 surfaces, the K value will be 0.5. Higher the K value, poor is the metal, dirtier is the metal. The first notch catches initial inclusions and the second catches remaining, so on and so forth. So the larger inclusions are caught in the first early notches and the finer inclusions reach up to the last notch. Again, it's an indication that if inclusions are found even in the last notch, metal is dirty. Next slide, please. This is how the fractures look. And you have to see all those 10 fractures, not only 4. Next slide, please. The second method of predetermination is pre-fill and portfa. Actually, these are 2 parallel studies based on the same concept or similar concept. That's why later on, these concepts got merged. On the left-hand side and the first image on the left-hand side, step 1. That is, there is a load cell on which an empty vessel is placed, which is evacuated, on which a utensil-like thing is placed, which has got a filter at the bottom. And a measured quantity of liquid metal is poured in it and the lid is immediately closed. The filter is very fine and it is pre-calibrated. It is designed in such a way that unless there is zero inclusion, it will not allow 100% metal to pass through it. It will choke halfway through or somewhere in midway. As the filter gets clogged or it gets choked, naturally the flow rate reduces, and at one point the flow rate stops or it becomes zero. These graphs can be calculated from the load cell and the timer being connected to the PC. So these graphs are called as pre-fill curves. Now, what is PODFA? That is porous disk filtration apparatus or porous disk filtration analysis. This particular disk or the filter which is placed at the bottom, that is the heart of this particular principle. It is designed to choke, and once it gets choked, the metal is solidified, that sample is taken out along with the filter. That's the fourth image. And the vertical section of that particular sample is seen under the microscope. The number of inclusions seen above the filter are 10,000 times more than those in the actual metal. So you get a quantification of that. But to solidify that metal, to take a section, to polish it, and to analyze it under microscope using image analysis, it takes minimum half an hour to 1 hour time. And when the liquid metal is molten and ready for pouring, we just don't have that time. Whereas the pre-fill curves, which is the earlier part of this particular study, it gives you online or instantaneous solution, which can be directly correlated with the number of inclusions. Hence, pre-fill is a practical study which is supportive and which is used on shop floors. And PODFA gives you quantification, gives you number of inclusions, but that is for academic purpose. It doesn't have any practical significance. Next slide, please. The pre-fill test uses the flow rate of molten metal through a microfilter at constant temperature and pressure as a measure of quality of metal. Very clean metal flows quickly, giving a steep, straight line in the test output. Inclusions in the metal such as oxide films quickly build up on the filter surface during the test and reduce the flow rate through the filter. Next, please. This is a sample of typical pre-fill curves. The first curve on the top is of a fairly good metal with minimal inclusions. Second curve, it gets slightly depressed. So naturally it has got some more inclusions. The third curve, it got flattened halfway through. So it has got more inclusions. The fourth curve, it flattens very early. So it has got coarse inclusions and lots of inclusions. Next slide, please. This is explanation of PODFA. When the pre-fill filter clogs, some metal remains above the filter and solidifies. The filter along with the residual metal is then cut, mounted, polished, and analyzed by means of an optical microscope with image analysis. Inclusions in the metal are concentrated at the filter surface by a factor of about 10,000. So total inclusion is expressed in mm square per kg. Next slide, please. This is a typical representation of microstructure as seen of the PODFA sample. Next slide, please. There is third method of predetermination of inclusion level, which is called as Limca principle. Now, this is not the famous cold drink Limca. Limca is liquid metal cleanliness analysis. Li is one word, that is liquid, M for metal, C for cleanliness, and A for analysis. On the right hand side, in the circular figure, just imagine that the beaker is a crucible and the test tube inserted in it is a sample tube. It's a refractory tube with a very small aperture at the bottom. And it is immersed in the liquid metal. It has got a lid. It is evacuated. Through the lid, there is an electrode placed in it going right up to the bottom of the tube. There is another electrode in the liquid metal in the crucible. As we all know, aluminum in any condition, in any state, is a good conductor of electricity. So this liquid aluminum itself becomes a conductor. And cross-sectional area of that orifice or cross-sectional area of that small hole at the bottom of the tube, it becomes area of the conductor. We also know that aluminum oxide or alumina is an insulator. It's a basic material for ceramics, porcelain, which is an insulator. So you have got a mixture of insulator particles suspended in a good conductor liquid. When you apply vacuum to the tube, liquid aluminum gets sucked into the tube through that small orifice. And once contact is established between the two electrodes, you get a current and a voltage at the ammeter and voltmeter. Once there is some small particle of oxide momentarily passing through that orifice, that oxide, which is an insulator, it eats up or takes away the area of conductor from that orifice. And naturally, you see a pulse in voltage as well as a pulse in current. More the number of pulses, more is the number of oxide inclusions in that particular sample. Higher the amplitude of pulses, larger is the size of that particular oxide inclusion. So you get to know how much and how worse is the oxide content in the liquid metal in a very short time. Next, please. This is a very explanation of whatever I said. The system consists of a closed glass tube and a small orifice in the tube. The duration of the pulse is related to transition time of the inclusion. The voltage pulses are amplified and their amplitude measures digitally. The size distribution and total concentration are displayed in real time on the computer screen. Next, please. This is photo of the Limca apparatus. Both these processes, or all the three processes, we have seen for predetermination of inclusion level or predetermination of cleanliness, or how oxide free is the metal. All these three methods are unfortunately patented by foreign companies. K-mold original copy is available at less than 30,000 rupees, but Portha prefill is available at a nominal cost of about 70,000 US dollars. And Limca is also available in India at a cost of about 80,000 US dollars. So very sophisticated and high-end foundries like HAL Foundry in Bangalore or PTC Industries, those kind of foundries which produce aerospace and defense components. There are hardly 2 or 3 installations of Podfa and Limca in India. But K mold is quite popular and it's a good indicator of cleanliness of liquid metal. Now, what is effect of clean liquid metal on mechanical properties of the casting? As I discussed earlier, it achieves homogeneity of the casting. Your casting becomes more reliable. The difference between test bar properties and the casting properties is negligible. Because oxide inclusion is a non-homogeneous entity. It's a foreign body. And to remove that, we have to perform this particular metal treatment that is called as cleaning or cleansing. Herein, we complete the first part of metal treatment, that is cleaning or cleansing. Are there any doubts or questions? You are free to ask. If there are no doubts, we move on to second stage of metal treatment. Next slide, please. The second stage is degassing. Hydrogen gas dissolves in molten aluminum to a great extent, and this gas remains within even after the solidification. This leads to a very common defect called as pinhole porosity, which reduces the strength of casting, and also casting fails in pressure tightness, casting leaks. Next slide. This is how pinhole porosity appears. It looks. It is spread all over because it is basically coming from the liquid metal itself. Do we have hydrogen in pure form in atmosphere? The answer is yes, but its content is very, very little. But we have moisture in abundance, humidity in abundance. And what is water, or what is humidity? What is moisture? It is H2O. So at higher temperatures, anything more than 600 degrees Celsius, H2O dissociates into hydrogen and oxygen. So in case of humid conditions, gas pickup and pinhole porosity increases. Next slide, please. In this graph, we can see that solubility of hydrogen increases 10 times, 20 times, or even more at about 660 degrees Celsius. That is at the liquidus. Everybody knows that when a solid metal gets converted to liquid, the intermolecular gap increases. The vibration between the molecules increases. That's why the metal becomes liquid. Naturally, hydrogen gas finds its place between those gaps. And that's why this solubility gets increased. Next slide, please. Removing dissolved hydrogen from metal, liquid metal, is called as degassing. Degassing can be done by 2 or 3 means. First is by immersing a tablet which emits chlorine or nitrogen. Second is by purging or passing inert gas like nitrogen or argon. Next slide, please. Now let us understand mechanism of tablet degassing, which was a very common degassing process maybe about 10 to 15 years ago. Even today, even nowadays, some foundries are compelled to use tablet degassing. The popular tablet is made of hexachloroethane. When This tablet is immersed in liquid metal. Due to high temperature, it sublimates. And product of sublimation. What is sublimation? Solid transfers to gas directly without stepping into liquid stage. Or if liquid stage is there, it is for a very, very short time. So in this sublimation, chlorine gas is emitted. This chlorine reacts with dissolved hydrogen and forms hydrochloric acid, HCl gas. Now we have seen that solubility of hydrogen is up to 2%, but solubility of HCl is 0%. So once HCl is formed, it comes out of the liquid metal directly. But along with that, aluminum chloride is also formed, and hence dross buildup or dross formation increases with this tablet. That's one drawback of this tablet. Next slide, please. It was a video of tablet degassing. Next slide, please. Now, the second disadvantage of chlorine gas or emitting anything chlorine is that it is hazardous to health of the operators as well as to the structure of the shed, and it's a greenhouse gas. Do you know how harmful chlorine is? It is 21 times harmful than carbon dioxide. So 1 ton of chlorine emitted is equivalent to 21 tons of CO2 emission. So in CBAM terms, the carbon footprint of chlorine is 21 times larger than CO2. Hence, it is extremely dangerous and extremely harmful gas, not only to the environment, but to the health of operators and to the metallic structure that trusses the sheets of the shed itself. To deal with it, nitrogen degassing by purging or passing or by rotary degassing is done. Some manufacturers have come up with nitrogen emitting tablets also. But my personal opinion about these things, the tablets, nitrogen tablets, is not very satisfactory. They do not deliver consistent result. Sometimes it gives good results. Sometimes it fails to give good results even after 2 or 3 tablets. So I reserve my comments. There are no allegations to any manufacturer, but I have explained my personal experience. Next slide, please. This was a video of rotary degassing. Unfortunately, we cannot see that video because my laptop is having some problem connectivity to Teams. Next slide, please. Now, application of granular flux during nitrogen degassing. For all those people who are doing nitrogen degassing or rotary degassing, normal experience would be that nitrogen degassing or rotary degassing takes about 10 minutes to 20 minutes, depending on the gas content in the liquid metal and quantity of liquid metal. If we use powder fluxes, then powder fluxes lose their effect within maybe 3 to 5 minutes. And so for later 5 minutes to later 10 minutes, whatever the time of our degassing is, the liquid metal is exposed to ambient air. In the first few slides, we saw that in induction furnace, it is not suitable for aluminum melting because of high gas pickup during churning action, due to churning action. Also, high exposure to atmosphere leading to high oxide formation due to churning action. Here, in case of rotary degassing, we are churning metal using the rotor. So, which is against the principle of good melting. So, flux should be present during the total time cycle of nitrogen degassing. Because the flux floats on the surface, it forms a liquid cover layer which prevents contact of ambient air with aluminum metal. Also, advantage of this churning with flux is that more and more metal comes in contact with the flux cover. The flux gets time and flux gets chance to react with the embedded aluminum oxide, and we get a further cleaner metal. Granular flux, due to its high bulk density, does not get wasted and moves along with the metal, giving controlled release for the total time cycle of degassing. Usually granular fluxes last for about 15 minutes. If unfortunately the degassing cycle exceeds 15 minutes, then you have to add on or top up granular flux once again. Next slide, please. This was a video of rotary degassing along with granular flux. Next slide. Next slide. Now, again the same question. Can we predetermine gas content or dissolved gas content, which is the hydrogen, before casting? Answer is again yes. Again, there are three methods of predetermination. First is visual inspection of solidifying metal surface. In this case, you take a refractory brick, which is a bad conductor of heat. You pour 1 spoonful of liquid aluminum on it, and some skilled person should observe the surface of that aluminum till it solidifies. It takes about 1 minute or 2 minutes maximum to solidify. During that time, if you observe small tiny bubbles coming to the surface and solidifying, then the liquid is having some gas. This particular method cannot predict how much is the gas. Again, it is subject to personal error, human error. One person might notice some gas, one person might not notice that gas. So it is subjective method. But if some foundry has got this practice, I am satisfied in one way, because at least that foundry is aware that hydrogen gas dissolves in metal, and we have to observe it, we have to see it. Whether they are successful in doing it or not, whether they give result or not, that's a different issue. But awareness is the first step towards quality. So if they are even visually inspecting the liquid metal, that means they are aware of this process. Next slide, please. Next. Now, this is a visual. This was a video. What you are seeing is just a initial first frame of the video. Liquid sample being taken into vacuum sampling machine or reduced pressure test machine. Next slide. Next. Previous. Various degrees of gas level as observed in the vacuum sample or the reduced pressure test sample. The density index analysis. It's an equipment which contains two stages. First is the vacuum sample or the reduced pressure test sample, wherein a predetermined geometry of a cup is made, which is the international standard. In that cup, aluminum liquid is poured. It is placed in a vacuum chamber containing a partial vacuum of 80 millibar. It is allowed to cool there. A second sample is taken in the same cup, but it is allowed to cool in natural condition, at atmospheric condition. As we know, the liquid aluminum is at atmospheric condition, that is 1 bar pressure, 1 atmosphere pressure, close to 1 bar. So naturally, the gas dissolved in it is also at 1 bar. If we take this sample and put it in vacuum, partial vacuum, 80 millibar, then the relative pressure difference between the embedded bubble of 1 bar and atmosphere of 80 millibar is very high. So naturally, these bubbles grow in size, just they bloat like a balloon. Some of them escape to the vacuum, but majority of them get entrapped because the aluminum sample is also solidifying simultaneously. So if you take a section of it, section of that vacuum sample, then what you see is in front of you. The top left is a good casting, a good sample. Density index will be around 1.5 to 2.5. The second sample is slightly dirty, slightly gassy. The density index will be around 4.5 to 5.5. The third sample is further gassy. The density index will be around 8 to 10. Fourth sample is further gassy. The density index will be around 12 to 14. And the last sample on the bottom right, is the dirtiest sample, gaseous sample, in which the density index is between 15 to 18. Now, what is density index? We have seen that under vacuum or under partial vacuum, the gas bubbles expand like a balloon. And that's why the solidified sample occupies larger volume for the same mass. So its density reduces. We are taking another sample in ambient air, which is not under vacuum. So it solidifies naturally and it represents its natural density. So the difference between the density of air sample and the density of vacuum sample, expressed as percentage of density of air sample, is density index. It is expressed in percentage. Higher the density index, more is the gas content. Lower the density index, lesser is the gas content. This particular process of density index analysis can be completed within 5 to 6 minutes, and hence it is a practical shop floor test and it has become very popular. Next slide, please. This is the third method of gas detection, which has got a sniffer. There is a probe which is put inside the liquid metal 24/7, and at regular intervals, it takes a sample and analyzes how much ppm gas is there. This particular apparatus is again patented and it is very, very expensive. On the left-hand side is Alscan, which is a patented product of ABB. On the right-hand side is Alspec H, which is a patented product of Foseco. Alscan is available at about 30 lakh rupees. Alspec H is available at about maybe 15 lakh rupees. But the problem with both the machines is that its probe is consumable and it is very expensive. A single probe gets eroded or corroded within maybe about 12 to 18 hours. And it costs not less than 30,000 rupees. So again, it's a fancy equipment and it is available only with very elite foundries like HAL. But density index analyzer along with reduced pressure apparatus is available at price range between 3 to 7 lakh rupees. Some of the fancy equipment like Ideco or others are further expensive. They are European made, but there are Indian makers who make these machines, and 3 to 5 lakh rupees is the price range. So, and they are quite effective, quite quick. So you find a lot of population of density index analyzers in Indian foundries. Next slide, please. This is a typical graph of automatic degassing cycle connected with Alspec H. It is taken from Foseco Alspec H brochure. I must mention that. And it gives you a clear-cut indication that how a digital signal can eliminate human interference in degassing process. At this particular slide, we have come to an end of second stage of metal treatment, that is degassing. This is also associated with homogeneity of casting. Hence, if you want a reliable casting, predictable mechanical properties, it has to be clean from oxides and clean from gas. You should have a homogeneous casting. Any questions up till now? Okay, if there are no questions, we move on to the third stage, that is grain refinement. Next slide, please. Give me a short break. Whenever a metal solidifies, the solidification begins from the mold wall. And from there, the solid front progresses to the interior of the casting, to the center of the casting. Naturally, whenever there is thermal expansion, conversely, there is thermal contraction. So liquid to solid contraction exists in all metals. In case of aluminium, depending on the grade, it may vary from 1.6% up to 4%. But normally, if we take it around 2%, then naturally there is a gap of volume between liquid and solid by 2%. The liquid will occupy 2% more space than the same weight of solid. So if our casting is solidifying from all the six, imagine a cube. It has got 6 faces, 6 sides. So solidification will begin from all those 6 sides and eventually end at the center of the cube. So whatever 1.65% or 2% is the liquid to solid contraction, that will get concentrated at the center of the cube. Because solid front will grow, and at one stage, there will not be any liquid available to solidify, and there will be a vacuum or void of 2% volume of that total cube at the center of that cube. That is called as shrinkage cavity. If we want to reduce effect of this shrinkage, what is necessary? That instead of solidification being initiated at only 6 walls of the mold, can we initiate solidification all over from within also? The answer is yes. There are artificial solidification sites or foreign solid particles which we can make suspended in the liquid aluminium. The most common particles in aluminum metallurgy are of titanium and boron. So if we add titanium or boron or both, their intermetallic compounds get suspended freely and solidification begins at those sites also along with the mold wall. So naturally, instead of 6 solidification phases, if there are 10,000 particles of titanium boron in it, solidification will begin at 10,000 locations. And if we are considering 1 liter or 1,000 cubic centimeter of aluminum mass, aluminum volume, then 2% of it, that is 20 cc, will be the eventual shrinkage cavity. If there is no nucleation and solidification is beginning only from the mold wall, then this 20 cc will get concentrated in the cube center. But if I initiate solidification artificially by inducing grain refiner, and in this process, I am able to create 10,000 nucleation sites or 10,000 solidification sites, then this 20 cc will get distributed at those 10,000 locations. So its severity will reduce to 1 by 10,000. It will be negligible. Although the volume of that shrinkage will be equivalent to the volume of initial shrinkage, but just because it gets distributed all over evenly and its individual appearance is minuscule, it becomes redundant. It doesn't have any significant effect on your mechanical properties. Whereas if there is concentrated shrinkage cavity, then you get abrupt failure. This process of inducing nuclei artificially is grain refinement. Next slide, please. This is the write-up of whatever I explained. The metal thus solidifies in all parts piece by piece. Each solid particle is called as a grain. More the grains in a given volume, smaller or finer are the grain size. These fine grains impart better strength to the casting. Hence, grain refinement not only avoids shrinkage, but also increases mechanical properties of the casting. That is the strength, that is UTS and YS. It can be done by salts or metallic grain refiners having titanium, boron, or sometimes carbon. The Japanese foundries are using carbon in some cases as grain refiner. I have not witnessed it because I was not allowed to visit it. But in India, Maruti Suzuki has got their own captive foundry in their Gurgaon plant. They are using carbon in some critical castings for their cylinder heads. But I have not witnessed that. I am not allowed to do that. Next slide, please. Can we check grain refinement visually? Yes. You take a button sample, just polish it on a fine sandpaper, dip it in etching agent. Etching agent is, in this particular case for grain refinement, is Tucker's edge. Tucker apostrophe S H ETCH. You can Google it. It's a mixture of hydrochloric acid, nitric acid, and sulfuric acid and water. You dip this finely machined or finely polished specimen for 20 seconds in Tucker's edge and wash it immediately. Allow it to air dry. Do not wipe by hand. If necessary, pat it, clean it, dry it by using a tissue paper without wiping. then these grains get revealed immediately within 5 to 10 seconds. So this is a quick test, shop floor test. You can have your own button samples, master samples ready with you to compare grain refinement. Next slide, please. Another method is further micro polishing it and observing it under microscope and defining the number of grains or the grain size. Next slide, please. This is ASM, American Society for Materials, grain size classification. That is the types of grains. These are macro graphs, MACRO, macro. That is what we saw with the Tucker's edge. Usually the sample size diameter is 25 mm, that is 1 inch. And whatever circles you are seeing, those are classified for 1 inch. Type 1 is finest grain. Type 6 is the coarsest grain. Next slide, please. If you have a microscope with image analysis software, then in that you directly get this ASTM macro grain size number. In this case, larger the size number, finer is the grain. These are available on ASM website. You can Google it, and I think Indian copy of this is available with Vardhan Works, Indian microscope manufacturer. You can ask them for a copy. They will give it to you. At this slide, we end our third part of grain metal treatment, that is grain refinement. Are there any questions? Just remember that first two stages, that is cleaning and degassing, have to do with continuity, homogeneity of the material that gives reliable results. This particular third stage, grain refinement, has to do with fineness of grains, increasing the number of grains in a particular cross-sectional area. In the audience, those who are metallurgists or those who have studied metallurgy must have heard a phrase called as slip energy. Whenever there is a fracture, it's dislocation of grains on a grain boundary. The energy required to dissociate or dislocate a grain from its boundary is called as slip energy. That slip energy is a function of that particular alloy system, and it remains constant irrespective of the grain size. So if you say 10 mm diameter test bar, it has got 1000 number of grains. Then to break that test bar, it will take 1000 units of slip energy. If I perform grain refinement, then the number of grains will increase from 1000 to 1200. So now to break that test bar, I will require 1200 units of slip energy. So if you perform grain refinement, your strength, your yield strength, as well as your UTS, ultimate tensile strength, both increase. Any questions? If there are no questions, we move on to the last stage of metal treatment, that is modification. Next slide, please. This is a small portion of aluminum silicon equilibrium diagram. the V shape. The bottom of the V is eutectic point. On the upside of the V is liquid. On the lower side of the V is the liquid plus solid. At bottom of the V, you see a horizontal line. That horizontal line is the solidus. The eutectic point in this particular graph is shown as 12.6%. On the left-hand side, you see that there is Al into bracket, that is a solid solubility, 1.65%. And there are three lines in color. First gives the solid solubility line. Then is the red line, which is a line representing 7% silicon, which is the most popular alloy, LM25 or ALSI7Mg or A356. All these three alloys come into the same segment, that is 7% silicon, 5.5% here and there. Next is ALSI9Mg, that's the blue line. That is another popular alloy. Now, the difference between solid solubility and the red line or blue line is the eutectic silicon. Whatever is in solid solubility, that silicon will appear in the alpha phase. Alpha phase is soft and ductile. It is seen as a white cell or white ellipsoid or a white amoeba-like structure under microscope. It is the first cell to form in case of hypoeutectic alloys. And whatever is the silicon in it. Now you can take the case of say 7Mg, the red line. It contains 7% silicon. Applying the lever rule. Those who are metallurgists will understand it very quickly. Otherwise, just remember that there is something called as a lever rule, and which defines the percentage of alpha and percentage of beta in case of any eutectic system. So at 7Mg, you can say that by lever rule, alpha and beta are equal, near about equal, 50%. So now if you take a sample of 100 grams having 7% silicon, then it has got 7 grams of silicon in it. If it is 50-50 alpha beta, then 50% of it, that is 50 grams of alloy, will solidify in the freezing range. That is between the liquidus, the upper side of the V, intersection of red line with the upper side of the V, and the solidus, that is intersection of the red line with the horizontal line. In this freezing range, one by one, these alpha particles will form. And just above the horizontal line, that is just above the solidus, 50% of aluminum alloy will be already solidified. It will be in mushy structure, a slush-like thing, wherein you find ice and water both together in fine grains, and it becomes a slush. So in that slush, there is 50% alpha, 50% beta. Now, what is alpha? Alpha is already containing 1.65% of aluminum. 1.65% of silicon. So 50% and 1.65% of it. That is close to 0.82% of the total. So we have got 7 grams of silicon in the total system, out of which 0.82 grams of silicon is utilized by alpha. So now 6.18 grams of silicon is remaining in the remaining liquid. And once we go down 1 degree below the solidus, that particular silicon will immediately solidify along with aluminum. That is the eutectic silicon or the free silicon. The appearance or nomenclature of this particular silicon plays an important role in mechanical properties as well as some defects in case of aluminum casting. Next slide, please. Now, in earlier explanation, we saw that it has got 7 grams of silicon in 100 grams of liquid, out of which 0.82 grams got solidified in along with total 50 grams of liquid. So in the remaining 50 grams of liquid, which is a part of the slush, we have got 6.12 grams, 6.18 grams of silicon. That comes close to about 12.5 grams or 12.5% silicon. So initially it was 7% silicon. Alpha took some part of it, solidified, and now it expelled the remaining silicon into the liquid. So now the remaining liquid has got this 13%, 12% to 13% silicon. That silicon during solidification comes out of solid stage and solution and starts segregating in form of platelets or needles. Just imagine a pile of wafers. If you take a section, you find that it's a line, a sharp line like a needle. But if you look it from a top view, it appears like a platelet. So in this case, if these platelets or needles are randomly distributed, they are harmless. But if there is some iron impurity, then the iron magnesium silicon intermetallic compound plays a crucial role in this, which makes these platelets or these needles specifically oriented. And in that case, a crack may propagate along with it because these needles are of silicon. What is the nature of silicon? It is hard and brittle. What is nature of alpha? It is soft and ductile. So as long as there is a uniform mixture, uniformly distributed hard particles in the soft matrix, you get a tough metal. But if those hard particles, those hard platelets get arranged in a single plane or close to a single plane, then it creates a fracture plane. So casting can get cracked at that location and it may get weak. Next slide, please. There are certain elements like sodium, strontium, antimony, phosphorus, bismuth, calcium, etc., which, if added to metal in small quantities, the nature of silicon changes from platelets or flakes to a bundle or a globule. This is called as modification of silicon. Those people who are conversant with ferrous foundry practices, this is something close to magnesium treatment. We convert flake graphite to nodular graphite. In the same way, by adding any of these elements, we can convert flake silicon or platelet silicon to a small bundle or to a globule. It begins with stubbing, that is some fragments, fragmentation, then microfragmentation, and then dispersion. Now looking at these elements, antimony is a heavy element, so it is avoided in any castings. Bismuth is also a heavy element, it is avoided. So although they are modifiers, they are not being used. Calcium is not a heavy element, but calcium is a known element which attracts micro shrinkages, and hence the component fails in fatigue test or endurance test. Hence calcium is also avoided. So now what remains is that sodium and strontium for hypoeutectic and phosphorus for hypereutectic alloys. So popularly only these three elements are used for modification: sodium and strontium for hypoeutectic alloys and phosphorus for hypereutectic alloys. Next slide. On the screen, you see the micrographs. On the left-hand side is unmodified, on the right-hand side is modified. These micrographs are taken by me, photographed by me, sample is prepared by me, the casting is produced by me, so there is no copyright infringement. Next slide. Array of lamellar silicon, which is unmodified silicon, inviting shrinkage. You see a black shrinkage cavity, which is associated with specifically oriented lamellar silicon, that is unmodified silicon. Next slide. Fully modified silicon structure. The white globules, what you see is the alpha, and the dotted gray part is the beta or eutectic. Next slide. Now this is taken from the ASM. So I must mention that it's not my property. ASM classification of types of modification. Type 1 is unmodified and type 6 is super modified. Usually in case of gravity die casting or LPDC or any other popular casting methods. Type 3 is easily achievable. Type 4 requires some special care. Type 5 is something is difficult to achieve, but even then we can achieve it, and it is used for defense and aerospace industries. Type 6. In my career, I have not seen a single sample of type 6. Till now, it is only on the lab scale. Next slide. Is the description of those types. Type 1 is fully unmodified silicon, is having a large plate, acicular particles. Type 2, lamellar silicon, both lamellar and acicular. Type 3, partial modification is done. Lamellae begin to break. Acicular silicon prevails. Type 4, which is easily achievable, I would say. 3 and 4 are easily achievable. Non-lamellar, most lamella are broken, few acicular particles. Now herein, I would like to ask you a question. How many of you are doing LM25 or A356 or ALSI 7 mg castings? And what is the maximum elongation you have witnessed from your own test parts? Anybody? Okay. Let me tell that usually 2.5%, 4%, 5% are the figures expected from the test bar for elongation of A356. But with proper modification, I have witnessed 19% to 23% elongation from the test bar with a UTS of 480 up to 530 megapascal. Next slide, please. No, previous. Previous slide. Thank you. So with this, we come to the end of our session on metal treatment. A quick recap. Cleaning and degassing take care of homogeneity of the material. Grain refinement increases the strength, yield strength and UTS. And modification increases the elongation. Grain refinement and modification both put together increase response to the heat treatment. So if you want predictable and good mechanical properties out of the casting, which exceed the standard limits, then proper metal treatment is the only way to it. There is one more mechanical property, or rather physical property, which is called as electrical conductivity. There is a specific grade of castings which require minimum electric conductivity of 33% ISCS up to 35%, 36%. There are various ranges. So if you want a better conductivity, go for proper degassing. A gas-free and more homogeneous metal gives you a conductive metal. With this, I come to the end of my presentation. Are there any questions? Please speak up. Yes, please.
Yeah, this is Narayan here. Yeah,
Yes,
can you
Mr.
hear me?
Narayan.
Yeah.
Yes,
okay.
I can hear you.
I was actually also hoping maybe today's session will cover the heat treatment processes. Maybe there can be another session on that, maybe.
There can be another session. You can request Mr. Chennai chapter office bearers, because I have got a bunch of material on heat treatment for various alloys, including the typical cycles recommended by ASM. Because heat treatment doesn't come under metal treatment, that's why it was not included in it.
No, I understand. Yeah, I
Yes.
didn't understand first. I was looking forward to that because we are furnace builders. We do drop bottom solutionizing furnaces and aging furnaces. So,
Now, what is the quenching delay for your drop bottom furnace?
sorry,
What is the quenching delay
we do
for your drop bottom furnace?
even as low as 5 to 7 seconds we have done.
Okay, but practically, what is achievable?
It depends on the size of the furnace also. We have done
Say one furnace.
drop bottom furnaces up to even 10 metric ton capacity we have done. And
So practically, you can say that 1 ton to 1.5 ton furnace, what is the trap?
Yeah, we can easily do less than 10 seconds.
That's very good. That's really good. I appreciate that.
Yeah.
Because those people who are having some queries on heat treatment, variation in hardness is mainly due to quenching delay. And if quenching delay is less than 20 seconds, this thing is eliminated. Second is that variation in hardness may occur due to improper quenching itself. That is, some part of the basket is within water and some part is not within water. Water level is not maintained properly. So quenching delay is the greatest parameter to control properties after heat treatment.
Yeah, when we get drop bottom furnace orders, quenching delay is a key performance parameter we have to prove. So, yeah.
Along with that, if you can add on to water level monitor and alarming system, it will be a added feature to your furnace. Because usually water level in the tank is left to the purview of the supervisor. And here, if you have a sensor in the tank, you can put a Pokai OK, so that if water level is inadequate, the furnace will fail to drop.
Yeah, we actually have temperature monitoring, but the water level, you are right, we leave it to the...
Every furnace has to be mapped, not only monitoring. Initial mapping has to be done, thermal mapping.
No, I mean the water temperature.
Water temperature monitoring is okay, but water level also you incorporate, that will be added feature I am suggesting you.
I think that's a good idea. I will note it down. Maybe we actually leave it to the supervisor for the water level. So maybe we can monitor in the PLC. Yeah.
Yes. Any other question?
No, sir, this is Gautam here from GR Metal.
Yes, Gautam. हाँ बोलिए.
I also joined. I got a from my Chennai friend. He just requested me. Good to see you after a long time.
Yes, indeed. Very long time.
I have one query. We want to make or develop some alloy. You know, we are in recycling industries. In that alloy,
both your units. I've been to Kadi as well as in Chhatra.
I know. So in that alloy, we want to get tensile as 250 plus and elongation 5% plus.
Right.
Okay. If I say the typical alloy composition, it is silicon is around 8.5 to 10.
Okay.
And Fe is 0.15 max. Copper is 0.03 max.
Okay.
Mn is 0.55 to 0.8. Mg is 0.15 to 0.35. And rest is you can say as a trace element 0.1, 0.15. And titanium is 0.1 to 0.2.
Okay.
So what you suggest? What are the modification treatment we want to do so we can get the better?
If you want to get 5% elongation, then it has to be at least type 3 modified. For that, you need to maintain strontium level of maybe 0.01 to 0.015.
Okay. We want to do the treatment.
Modification level comes.
Okay. We should do the titanium boron modification also.
No. Titanium boron is grain refinement. That is for achieving 250.
Okay.
So if 250 is easily achieved, that I don't think there will be any problem. Your problem will be mainly in achieving 5% elongation. Am I right?
Yeah, that is the measure here. And for your information, in some ADC12 alloy ingots, we get 4% elongation. Normal ADC12.
That's right. Yes.
But in that case, ADC12, in that case, we achieve only 180, 85 as the tensile.
Okay.
So here the tensile requirement is 250 and elongation is 5%.
That is the importance of metal treatment, na? That's why.
Yeah. So you are suggesting strontium.
in this alloy, normally are you getting strength and you are not getting elongation? What is your pain? What is the pain area? Or you are not getting
First
both?
time, no, we did not achieve both. We are, you can say around 3.5% elongation we have achieved, and this tensile also 210 to 15 like that we have
Okay.
achieved. We failed by both the parameters.
Then there are three important parameters to it.
Okay.
After complete melting and your final chemistry,
Mm-hmm.
add titanium and boron.
Okay.
That is
Okay.
TIB.
Yes.
Keeping objective of titanium at 0.15 or 0.17%.
Okay.
Do not exceed temperature of 780.
Okay.
That's max.
Okay.
That is why I said that silicon, let it dissolve completely. Then you may put off the burner, drop the temperature to below 780,
Okay.
then add titanium,
Mm-hmm.
maintain it to below 0.2, but
Okay.
above 0.15. That's why I said 0.15 to 0.17 is good enough.
Okay. Got it. Got it.
And
Also,
then add strontium, targeting 0.011012 up to 0.15.
okay.
And this should be done after degassing.
Okay.
Once degassing, you have to maintain the DI below 10%,
Okay.
and then add titanium, then add strontium, and then start pouring.
Okay.
In this case, your pouring has to finish within 1 hour.
Okay.
So if the pouring lasts for more time, then you have to check DI again
Okay.
and correct it by degassing.
Okay.
Yes.
That means, for example, if our liquid is 10 tons and we are expecting around 5 tons per hour is my casting rate.
Right.
Okay, that means in between I have to
You
do
have to
again
perform
degassing.
degassing once again.
Okay, after degassing also we do the modification. Is
Need
it
not
required?
be, because strontium modification lasts for about 3 to 4 hours.
Okay.
Huh.
Okay, good enough. Okay, thank you.
Yes, thank you. Yes, Mr. Venkatesan.
Hello, sir.
Hello, yes.
Sir, we are processing aluminum sand casting, sir.
Yes.
For that, what will be the best pouring temperature, sir?
What is the
Metal
wall
pouring.
thickness?
Wall thickness will be around 8 to 12 mm, sir.
Okay, and which is the alloy?
ALSA 7mg.
Okay. And
C4CH. Same as ALSA 7mg.
all right, all right. Depending on your gating, it can be between 680 to 700.
Okay.
Yeah. There is no need to go more than 700.
Okay, sir.
Currently, it is safe to go up to 740, 740. But with 8 mm wall thickness, it will be good enough to pour it at below 700.
But for 700 degrees Celsius, we are facing unfilling of the
Then
casting, sir.
increase the number of gates.
Gates. We need to
Increase the
gates.
flow rate. Increase the flow rate so that it can be accommodated.
Okay, okay, sir.
Yes.
Then another one, busters, sir.
Another question, if you are doing sand casting, then you have to do modification by sodium.
But we are doing by strontium, sir.
You will get a repeated problem after some time.
What will be the problem?
When you use those same returns, runner riser or rejected casting,
Yes.
after second or third remelting, you will get problem with strontium. So for sand casting, my request is to go for sodium.
What is the percentage, sir?
Sodium will be 0.005 to 0.01 final chemistry. That is not visible in spectrometer. You have to add the sodium salt as per manufacturer's recommendation.
Okay.
Sir.
And also we are facing a bus test failure, the same type of parts.
Yes. So that means you are into electrical industry.
Yes, sir.
Yes.
For the energy.
Okay.
Yeah, for electrical application we are manufacturing.
GIS components.
Yes, absolutely.
Okay. So GIS components require very special care.
Yeah.
Right from the first stage of cleaning.
Okay.
All the 4 parameters of metal treatment have to be done meticulously. There should not be any impurity in the alloy. Iron content has to be critically monitored.
Okay.
Yeah, means your density index has to be below 3.5 always.
Now we are maintaining for below 1.
Okay.
Okay. And what will be the ferrous or iron element percentage?
Iron should be below 0.18. Below 0.2 compulsory and preferably 1718.
But we maintain the whatever parameter you said we maintained, but then also we are facing this failure, burst test.
All right. Is it repeated failure at the same location or location varies?
Our location varies.
Okay. Then it's due to some casting defect.
Due to some casting defects.
Yeah. And if location varies, blowhole or sand fall,
Okay.
which disturbs your wall thickness. That might be the main reason.
Then what has to be done, sir?
You are into resin coated sand or green sand?
Resin
coated sand.
Resin coated sand.
All right. Are you applying any further coating on it? Zirconia coating or?
Yes, sir. Zirconium.
Okay. Zirconia coating, apply double wash, point number 1, which will prevent. Thinner based zircon. Double coat. First coat apply, burn it. Second coat apply, burn it. After coming to room temperature, close the mold. That will eliminate any chance of sand fall, sand wash, as well as any blowhole from the sand. Along with that, provide sufficient venting from outside.
Venting.
Vent.
Oh.
Yes.
So that gas of combustion goes out immediately.
Mm-hmm.
The resin burn, that gas should not come into the casting. It should go out immediately.
Okay.
That venting you have to take care of. Third thing is that are you checking with K-mold?
No, sir.
No, sir.
No.
Okay. Then check with K-mold. The third probability is that there might be some inclusion in your metal which may float from here and there. So in the burst state failed components,
Okay.
you check the fracture visually.
Okay.
That will take you close to the root cause.
Mm-hmm.
If you find multiple cracks on the fracture, then it's a difficult thing. If you find a black dot or many small black dots, it is inclusion. If you find some shiny crystals, it is metallurgical defect, that is primary silicon.
Oh, okay.
Likewise, there are many parameters for the failure of burst state. It is not easy to solve in a conference call.
Uh-huh. Okay, okay.
Yes.
Okay. So may I have your number, sir, so that in future.
Yeah. 98228
1 second, sir. Please repeat, sir.
98
98
228
228
45
45
478.
478. Okay, sir. Thank you, sir.
Yes,
Thanks
you're
for-
welcome. Yeah.
Thank you.
Any other question?
The equipment for testing, like continuous monitoring of hydrogen and stuff like that. You said they're all patented. They are running to millions of rupees in value and the consumables. Are there any projects set up by the Indian Institute of Foundrymen with institutions like IIT or something to create this equipment in India, for example?
No.
You think it's a good idea? I mean, because there are a lot of scientific brains in our country to build this equipment also, right?
See, we have to change the path. Now we know that there are two methods by which we can sense it. These scientists have to find a third method, which is not common with these two. Then only we can get our own patent.
Okay.
Are you getting my point?
So you are saying that the very method is patented.
Yes.
So we can't follow the same
can't
method and
copy that
invent a
right
new
now.
machine for that. Okay.
Yes. And if you have noted those points, then you can Google it. Those patent documents are available freely.
Okay.
Yeah. I have gone through it and it is not possible to replicate it by some minor change.
No, the
You have to
idea
find
is not
another
to
way
idea
of finding
is
it.
no, idea is not to cheat the patent because we have to respect intellectual property.
Correct, correct.
But at the
So-
same time, we cannot be also so dependent on the Western world in terms of
Perfect. I got your point.
testing our method.
That's why the scientists should find a way to check. Now, I give you some analogy. What is K-mold? It is just common sense and simple observation.
Hmm.
You are from Chennai or which place?
I'm from Chennai, sir.
Okay, in Chennai, it usually rains a lot.
Yeah, a lot of humidity. Hmm.
When it rains, the storm water flows from the road.
Yes.
It carries a lot of dirt, lot of leaves and whatnot, plastic bottles and everything. Have you observed flow of that water? Wherever there is a turn, at a larger radius of that turn, all this dirt gets accumulated. Have you observed that? That's the very principle of K-mold.
Yeah, that's what you said in the last part. If there is still dirt, that means the metal is really dirty, right?
Correct.
After it has left
Correct.
out at every
So
turn.
after passing 4 bends, if something is left, it has come to the 5th bend.
Yeah.
That means it is really dirty.
Yeah, I got it. I was
So
understanding
now
that.
this observation, you have to observe something different now. Can you create a vortex in a small mold? In case of vortex also, there will be a separation of suspended materials. And then you can patent it in your own name. Are you getting my point?
No, I got it. I mean,
So
when
have
you
to
say
find
you to me,
another
I may not be
way
capable of.
judging it.
Yeah, I'm only saying for the scientific community in India should start looking at alternates for all these very expensive
Correct. Absolutely, I
equipment.
agree with you 100%.
Yeah,
But
yeah.
our scientists are not in mood to do it somehow.
Radhi, there is no further question. You can close the meeting.
Yep.
Sure.
Ramesh? Ramesh, Raj is there?
Yes, sir. Yes, sir. Rajmohan is also there, sir.
Yeah.
Thank you, sir. Thank you very much. Actually, on behalf of IIF Chennai chapter, extend a sincere thanks to Mr. Anant Bam actually for an excellent and insightful session on aluminum metal treatment and its effects on mechanical properties. Your expertise and clarity made the session truly valuable, sir. And a big thanks to all the participants actually for your active presence. Thank you very much, and looking forward actually in further sessions. Thank you very much.
Thank you. Thank you very much.
Thank you. Thank you.
As expected by the participants, let's have another session mutually on heat treatment of aluminium. If we can.
Surely, sir.
Yeah, that will be very useful. Thank you. Nice session, sir. Thank you.
Thank you, sir.
Thank you.
all.
Bye.
Yes.
Thank you.
All right. Thank you. Mr. Senthil, I will connect with you separately regarding Urja Sanchay project.